Okay, everyone, I hope your week is going well. And so you should be working on your quiz right now, hint, hint. Okay, do not wait until tomorrow. That gives me gray hair just thinking about it. Just a couple of administrative things. Today's lecture, you're only going to have one, and it's going to be reasonable length, relatively short. The reason is because I know you're working on your quiz. Okay, so I'd rather you listen to a short lecture today and then go focus on your quiz. The other thing, and remember, this class moves fast, okay? But it's summer term, it's the way it goes. You guys have got this. On Friday, I would like you guys to turn in a draft of your paper. So let's talk about this paper. As far as the parameters go, this, by the way, is a first draft of the paper for your project. Okay, so remember you guys are doing a project and each step is worth 25 points. We talked about that the first day of class. So you don't have to do a paper, though, for a format. I'd like you to actually do something more creative, like a web page or a podcast, because those are way more fun. But what the purpose of the paper is to give you a basis to pull your information from later. Okay, and so 2 to 5 pages, double space, 3 to 5 references, APA formatting. I'm not going to be super meticulous. If you turn in one paragraph, then I'm counting words and we got a problem. Okay, but overall, just get a draft together that you would feel comfortable sharing with your classmates. Now, I say it's due on Friday, but I'm giving you until Sunday night at 11:59 p.m. to actually turn it in before all of the papers go out to everybody to be peer reviewed. Okay, so make sure it's something that you're comfortable enough to turn in that you want to have your classmates review it. If you want to be anonymous, you can. Just don't put your name on it. I'll know that you turned it in because I can see what the system says. Okay, so again, 2 to 5 pages, double spaced, 3 to 5 references. Make sure that you have enough information that when you come up with your final project, whether it be a podcast or a web page or something along those lines, or a PowerPoint presentation, you don't have to give the presentation, obviously. You just would type in the notes what you would say for the presentation. You guys can have whatever format you want, but just make sure this paper has enough substantial information that you'll be able to easily pull from it for your final project. Also make sure it's decent enough quality that you'd be comfortable having your classmates read it. And remember that it's due Sunday night at 11:59 p.m. So that should be plenty of time for you guys to get a good solid draft together that you guys can review each other's papers. And if you have questions or something absolutely happens, I know it's summer, I know the crazy things are going on right now. If you're really stressed about it, let me know and we'll figure something out, okay? It's meant to be low-key, low stress, but it's a gentle nudge to get you guys to make progress on your project. Now, I'm not going to lie, today is one of my very favorite topics, fossils, okay? And part of what I love about fossils is I've been collecting them for as long as I can remember. When I was a kid, I always used to look on the ground, especially if there was a new limestone driveway that somebody was putting in or something along those lines, because a lot of times you can find a lot of cool fossils in there, and that makes it actually really awesome and really fun. So, okay, we have many different types of fossils, okay? And so they are called cast fossils. They can also be mold fossils, trace fossils, or what are known as true form fossils. So let's start at the bottom and work our way up. Okay, true form fossils, by the way, are the same thing as unaltered remains. It's the true form of the fossil. Okay, so basically we're talking about a frozen mammoth or an insect preserved in amber or something along those lines. It's the actual critter and material of the critter itself. Okay. Trace fossil. Now that's a fossil that it's evidence that a critter was there, but it's not like the actual critter. So footprints or a tunnel or what's known as coprolite, which is basically fossilized poop. Okay, so evidence the critter was there, but not the actual critter. Now let's talk about mold and cast, and we're going to talk about these because it's basically when you have one, you have the other. So let's give the example where we have a clam. Okay, and so a landslide covers the clam because it can't get away. And then sediments cover the landslide. Okay, add some heat and pressure, and gradually that turns to rock. A few million years go by, the area goes dry. Okay, there isn't a lake there anymore, but instead what happens is you have water coming and bubbling up from underneath, and that's groundwater. And by the way, this actually happens all the time. Let's say groundwater comes up from underneath and it's pretty acidic. And it happens to, let's say the rock is really porous And our fossilized clamshell in there is actually, our clamshell is dissolved because acidity can actually dissolve shells like that. So then all you have left is this empty space. That's called the mold because the empty space is in the shape of the clam. Think of a cake mold, think of a jello mold, think of something along those lines. Okay? Then let's say that the water table goes down again. Okay? And different water full of sediments happens to come up and submerge that empty hole or that mold. Well, let's say that that water has a whole bunch of sediments and so forth that precipitate out, or crystals, or something along those lines. And when it precipitates out, it fills that mold. That's known as the cast. Okay? Water table goes down, that cast is covered and hard like a rock. The mold is around the outside. Both of them preserve the shape of the fossil because, you know, it's based on the shape of what actually was that clam that was there at that time. I know this is a little confusing. I'm going to see if I can find some stuff online that might help with this. But I think for the most part, you know, just think of the mold like a jello mold. That should help. Cake mold, if you guys do any baking, anything like that. And then the cast is just the inside of that and something that precipitates out that fills that mold. Okay? If you have questions, let me know. Taphonomy is actually the study of the process of fossilization. Okay? Now, the process of fossilization is actually pretty tricky because things have to happen just right in order for a fossil to be created. Let's say you have, you know, some critter in red here that dies and sinks to the bottom. Which, by the way, a lot of times that doesn't happen because usually they get filled with gases and decompose, blah, blah, blah. Well, it sinks to the bottom for some reason and then gets overtopped with sediment. Okay? Overtopped with more sediment. Add some heat and pressure and eventually that turns to rock. Okay? Then what happens, all of the components that were once biological eventually structurally convert to rock because of the crystallization process and so forth going on in there. Then let's say that the fossil somehow, we have tectonic activity. And so in the picture 4, that lifts the fossil up, okay, and then you get some weathering of the rock, and that's how the fossil is actually discovered again. So you can kind of see that the process is, you know, has to be just right in order for something to be preserved. Because most of the time when something dies, especially if it's a land-dwelling critter, it gets scavenged or it gets eaten, okay? Or it decomposes or something along those lines happens. So a lot of times, many times things are not preserved in fossils. However, when the conditions are just right, it can happen. What I want you to get from this, by the way, is how a critter could be fossilized. So if you guys know that, you'll be good to go. When it comes to all natural remain or true form fossils, again, I mentioned this a little bit earlier, so a frozen woolly mammoth. Okay, so the mammoth dies, keels over, gets frozen, all right, gets preserved that way. Freezing is one of the best ways to preserve critters, all right. Another example is an insect in amber. So you're an insect, you're flying along, minding your own business, then all of a sudden a gust of wind comes up and it slams you against a tree, okay. Unfortunately, the tree's got a lot of sap, you get stuck there, you die. Then the tree eventually dies, takes you with it. The chemical composition of the amber and or of the tree sap changes over time. Eventually, it turns into a super hardened resin, and that's what amber is. Okay, so basically, it's hardened tree sap. So when it comes to amber, I will tell you I'm fascinated by it because it definitely preserves a lot of small critters really well. Realistically speaking, it's a hardened resin of a tree. By the way, unlike Jurassic Park tells you, it does not preserve DNA. Okay? Having been someone who worked in the field of ancient DNA, I had friends who tried to replicate the experiment for that movie, and they couldn't. All they were able to actually pull out, by the way, was bacterial contaminants. So what does this tell us? It doesn't preserve DNA. According to my husband, I'm no fun to watch movies with, by the way. I don't know if you guys have been watching on TV lately. There's a lot, I don't know, maybe it's just my generation that watches TV these days. Jurassic Park's been running a lot, and it's been killing me every time I've seen it. So when you're a scientist, somehow watching movies isn't as much fun anymore. But anyway, amber does do a really good job at preserving what an insect looks like. It just does not preserve the chemical molecular composition of the molecules that made up that insect. And that's why you cannot, extract dinosaur DNA from amber. Now, a few slides ago, we were talking about mold and cast and all of that, and those are fossil categories, okay? Now what we're talking about is processes of how fossils are formed. So this is basically the mechanism of how certain fossils are formed. One of them is known as carbonization. And remember, the list up top is not necessarily comprehensive, okay? So we're just talking about examples for each of these, and we're not including everybody. So carbonization, the best way I can think of to describe this is, let's say you have an oak leaf. Okay, now I don't know if you guys have gone wandering through campus in fall after all the oak leaves, or in your neighborhood, all the oak leaves are on the ground. And let's say it's been raining a little bit and maybe a little bit of sleet and all that, and you kick away a couple of oak leaves, but what you see on the sidewalk is a preserved shape of that particular leaf, okay? What's going on there is oak trees in particular have a whole bunch of chemicals in the leaves, and that's meant to deter herbivores from eating them. All right, and so, but those chemicals can leach out of those leaves. Well, this is kind of the same idea. So you have a leaf, it falls to the bottom of a lake, it gets sediment covering it up, okay? The actual leaf matter will decay, but what's left is a carbon outline of what that leaf looked like. That process is known as carbonization. Okay, because it's made up mainly of carbon. Now, other critters can do this too. Okay, leaves are a particularly good example of this, though, just because they have so many chemicals in them. Again, they're trying to fight off the herbivores. But that is one process and one way that you can have imprints of fossils. Now, another way that fossils can be formed is called permineralization. Okay, and so the best example that I can think of this is the petrified forest. Now, if you guys ever have a chance to go out southwest, if you haven't already, visit the petrified forest. It's so cool. Sorry, fossil geeks like me really like it. Anyway, the way that those trees were actually formed is through the process called permineralization. And so basically what happens is all the trees in that particular area were buried relatively quickly. Okay, and I can't remember if it was a volcano that did it, but something along those lines. Once the trees were buried, they died, of course, because they're not going to be able to live anymore. Well, the groundwater came up, okay, and eventually what happened is that the groundwater came up and it filled in all of the holes of the trees. Now, trees are very porous. There's a lot of holes in that wood, all right? All the holes were filled in. And when those holes were filled in, there was a lot of sediments and crystal that precipitated out. So when I'm saying precipitation, by the way, think back to the chemistry that you guys tried to forget a long, long time ago. That means there was a whole bunch of little solids in solution that came out to be solids and form crystals. Okay, so all of those crystals came out of solution and filled the holes of the wood. Eventually, the wood itself deteriorated, but what was left was, an imprint of it, in these crystals, which is actually pretty cool. I don't know if you guys are alive long enough to remember the negatives of pictures. Okay, like if you actually had film and a negative and so forth, this is kind of that idea, because it's, you have these crystals that are filling in the holes. Okay, but so they filled in all the holes of the wood, and then the wood actually deteriorated. So if that makes sense. But anyway, it's a really cool process. You're left with these beautiful crystal structures of this wood that existed there at one time. And yeah, if you have a chance, it's pretty amazing to see. Now, recrystallization, how this process actually happens is kind of in the name. So a second ago, we were just talking about permineralization, okay, where all of the holes in the wood would eventually get filled with crystal, okay, in sediments that would precipitate out. That has to happen first before you can have recrystallization. Write that down. Okay, so first permineralization, and sometimes that's where it ends, and they just stay permineralized, and that's fine. But we're talking about millions and millions of years here, and so that's not always the end of it for certain fossils. Some of them go on to the second step, which is known as recrystallization. So think back to the trees that we were just talking about a moment ago. Let's say that they'd stayed buried. Or here's a shell. Okay, it was buried at one point in time. It went through permineralization, so all the holes were filled in. It used to be beautiful crystallized fossil. Well, a lot of times what happened is those crystals are not necessarily the most long-lasting material. Okay, and so what will happen is one type of fossil rock will get replaced by a more stable one. Okay, so For example, many modern shells are made of aragonite. Okay, it's a form of calcium carbonate. So what happened is the aragonite will alter or recrystallize to calcite, and calcite is more stable. So basically what happens with recrystallization is you go from one form of a fossil, which is not as stable, to a more stable one. That's what I want you to get from this. Don't panic, okay? I just want you to kind of get the gist of how fossils are formed, because it's a really cool process and it's like super complex. And I might look at this rock and think, not cool, it's just a rock. But no, it's cool. First off, it was something that existed millions of years ago, which makes it super cool. And then secondly, the fact that the process of how fossils are formed can be pretty complex, also makes it super cool. If anything, hopefully you guys are getting a good appreciation for these crazy looking rocks the next time you see them on the ground. Now, replacement, this is the process that gives us the mold and cast that we were talking about earlier. Okay, so you have a shell, the critter dies, okay, add some sediments, add some heat and pressure. We talked about this before, it turns to rock. Then the water table comes up, dissolves the shell, you're left with the mold. Okay, water table goes back down, another water table filled with sediments comes back up, and you end up getting the mold filled in by sediments. That's known as the cast. Okay, but that critter, of course, is long gone, and the shell is long gone, but what was left completely replaced it, if that makes sense. That's thus the name. Okay, so again, we talked about this. This should be pretty, you guys should be pretty solid with this. If not, let me know. If you're anything like me, you want to know where you might be able to find fossils, because I'm always looking. And I would say, aha, that's an excellent question. Well, as you can see here, very often you can find them from glacial outwash, which is what that picture is to the right. It's of a glacier, because let's face it, glaciers drag everything everywhere. And so a lot of times they'll pick up rock from one area and dump it into another one. Okay. Other places you can actually find fossils in areas you least expect. A lot of our deserts that are deserts today at one point in time were underneath seawater. And so you just kind of have to get lucky, in a sense, to find where fossils can be found. But you also have to consider the type of rock, because limestone is a really good preservative for fossils. But of course, you're not going to find any fossils like in cooled magma or anything like that, because that would have, burned everything. So the other thing you want to consider is, the position of where your fossils might be found. And so again, we've talked about this earlier. And so, your fossils towards the bottom of an area are going to be older than those towards the top, keeping in mind sediments are laid annually, generally, in rivers and lakes and so forth. And so you just have to kind of keep everything in order to figure out who actually existed when. So areas where volcanoes erupt are also tend to be good ways to preserve fossils and so forth. So here we have some sections of trees. They're made of stone now. But what happened was about 3 million years ago, the trees were covered with ash abruptly. And so they didn't have time to degrade or anything else. And so because of that, ash also tends to suck all the oxygen out. And eventually they turned to stone and turned into fossils. So you just kind of have to know where to look. It's not always easy to determine where you'll find a fossil, but a lot of times there's some really good ones out there, the ones that we can find. So here's a question for you. Why is it that fossils are rock colored? This is a trick question. Okay, I'm telling you now. Why are fossils rock colored? Well, because they're rock. Okay, so in order for something to fossilize, the way we tend to think of traditional fossils, okay, it has to turn to rock. Now, this doesn't include unaltered remains; those are different. Okay, and there's exceptions to every rule. However, fossils are rock colored because basically they have turned to rock by the time point that we find them. So Darwin watched the fossil record very closely because he used this when he was figuring out his idea of natural selection and evolution. The problem is that there's a lot of holes in the geologic record, and so there was a lot of things that are missing. And so in order to deal with this is his quote, "Geology assuredly does not reveal any such finely graduated organic chain, and this perhaps is the most obvious and serious objection which can be urged against the theory." Of course, he's talking about evolution. "The explanation lies, as I believe, in the extreme imperfection of the geological record." So what he's saying is that the fossil record is very incomplete. Okay, and he knew this, and there's a lot of good reasons as far as why the fossil record is incomplete. So let's delve into this deeper. And what I want you guys to do is pause lecture, and I want you to think and write your answers as far as why is the fossil record so incomplete. Okay, so take a moment, stop lecture, and come up with your list for the slide. So there's a lot of reasons that the fossil record is incomplete. First off, we haven't found all of the fossils. Okay, so a lot of them are going to stay buried and will remain there, and we'll never find them. It's just the way it is. Secondly, tectonic activity can also destroy a lot of fossils. Okay, so when you have a subduction zone, remember that term should be familiar, or something along the lines where you have one plate sliding underneath another one, any fossils that are buried in that rock can take with it. Okay. Additionally, a lot of species are not necessarily preserved as fossils, because we said many times when you have an individual and it dies, it will get either scavenged by someone else or it will decompose. So you could also say that the fossil record is incomplete, and in addition to that, it is biased. Okay, certain taxa are preserved better, others are hardly preserved at all. So the fossil record is biased as far as taxonomy goes. Some fossils or some species were not actually preserved at all, or very few of them were. Others, a lot of them were actually preserved. So let's say you had a dinosaurs. You know, we do know we had a bunch of dinosaurs that were preserved over time, but not always the best species that was recorded. Clams, on the other hand, we know a ton about bivalves and clams because those guys could not escape. If they were going to get buried by a mudslide, everybody got preserved. Okay. Other reasons why the fossil record is biased is that most of the time it's only the hard parts that get preserved. So you had to have a shell, or you had to have a bone or something like that. Usually the soft material does not get preserved. Had to get buried. Okay, so this critter had to get buried just right, otherwise it was scavenged or decomposed. Additionally, you have to collect it. You know, some fossils will remain intact, some of them won't. Okay, and so a lot of times fossils are in parts of the world that humans don't really spend a lot of time in, others can be, it just depends. And then you got to find it. Okay, and a lot of fossils are really deep under the earth and they will stay there because we may never find it. What's interesting to think about, though, is that George Gaylord Simpson, if you remember him, we talked about him on day one, trying to bring everything back at full circle kind of deal. So estimated that we know maybe 0.03%, by the way, to 0.1%, that is not much, of all the species that ever existed. Okay, so basically so many more species existed than we will ever know, and we probably will never know. All right. But we do the best we can, we find the information we can, and we learn what we can. It's really all we can do. All right, so if you guys have any questions, I will be online tomorrow. I will set up the Zoom, the actual Zoom link so you guys can come talk. Remember, if it's a question about the quiz, please keep it general. If it's a question about the paper or something like that, I'm more than happy to help, and that's why I'm there. So, all right, you guys stay safe, and I will talk to you soon. Have a good night.